And yeah, as you see, this is going to be a topic about post-quantum cryptography or quantum-safe cryptography, or what you like to call it. So you might wonder what this has kind of relevance with the OpenSSL project or mission. And actually, as EJBCA, as Vlad mentioned, was started by me in 2001, and actually it was only possible because Bouncy Castle had been started before. So without Bouncy Castle, I couldn't have possibly done what I did. So that also altered the course of my life a bit. So let's get into it. So about post-quantum cryptography, it has been around for a couple of years now. So Bouncy Castle started with post-quantum cryptography in 2012, I've heard from David, and I've been doing it myself for a couple of years now. And well, since the dilithium, Kyber, and Sphinx Plus were kind of working names when the new algorithms were in draft. And why this is relevant for this interoperability talk is that at the beginning of this year, that was actually an issue because people or cryptographic modules were claiming to do ML-DSA, and you sent some data to get back an ML-DSA signature, but in fact it was a dilithium signature, which cannot be verified with an ML-DSA verification code. So, and vice versa, of course. So this, luckily, this phase is past us now. So I like to not see dilithium and Kyber a lot more now, but eventually it shows up in presentation slides and such, while they actually typically mean ML-DSA and ML-KEM, which I think it's, yeah, let's cross those old ones out. And there we are. So I'll start a little bit tracking kind of the standards. Typically, I recommend to not use things in production unless there are standards for it. We have standards for the algorithms now, as we know, ML-DSA, ML-KEM, SLH-DSA, and soon even more algorithms. But you actually have to use them as well. So we're working with PKI and certificates and such. So there's been a lot of involvement. So actually the standards are still in draft. They're not final RFCs yet. Even in the last couple of months, things change when it comes to ML-DSA certificates or storage of private keys. Now it seems stable, kind of moving on, hopefully soon an RFC. The same things with a lot of other things like SLH-DSA, ML-KEM, and those. There is actually only one final standard out there for post-quantum, which is a hybrid certificate, which is part of X509 since 2019. But that's kind of the standards which lesser people use. And yeah, so things have gone pretty fast in the standardization area, and we're actually starting to use things before they're in RFC. So there are also things like you have to put even certificates into use, and then there are other usage standards like TLS, ML-KEM, hybrid key exchange for encrypting the channel, of course using certificates for authentication. All of these are still also draft. There are not final RFCs yet, but specifically, or in particular, I would say ML-KEM key exchange is in production use across the internet. Normally, I wouldn't have recommended that, but in this, with the post-quantum cryptographic algorithms, things have moved a little bit faster, I would say, than we have been used to in the past. At least the good thing is that we have or will have fine, open, freely available and freely implementable in open source software standards pretty soon, which is a kind of a privilege working within the cryptographic and PKI community, is that we have always had very good standards to fall back on. So I found this current state of, or the heat map Oh, I actually had updated this too, because just before coming here, I found they had updated this to a September 2025 heat map. So you can see depending on different use cases, there's different possibilities, I would say, to use post-quantum cryptography. So for now, you can see TLS 1.2, there's no way, you can't do it. TLS 1.3, there's a couple of ones that have moved to broad adoption. I already mentioned hybrid post-quantum key exchange for encryption, while other parts are in various stages of readiness in order to deploy and actually use these things. So, but we all want to kind of get past this experimental stage, and that is what the majority of this talk will be about. So how do you reach interoperability? And there are kind of some basics or some base foundation, which is work that is being done in Internet Engineering Task Force, IETF, which does some basic foundational interoperability testing among many libraries. Bouncy Castle, of course, OpenSSL, and commercial vendors and everything. But further on, there's more project-to-project cooperation and interoperability testing. You heard that from Tim as well. And of course, commercial vendors do that. And everything, also kind of a privilege here is that it's usually very friendly co-opetition. So this is the front page of a book from the 90s, which kind of coined this term co-opetition, which means cooperation between competitors. So even though there's projects compete against each other, there's vendors that compete against each other, we all try to cooperate in a friendly manner because we know that we rely on things being interoperable and working in order to do things well. So getting a bit more deeper into the weeds about interoperability. So since we're working with PKI, which is, well, one layer on top of cryptography, but it's still not a use case in itself. You know, no one uses cryptography just for cryptography its own sake, and no one uses PKI and digital certificate just for its own sake. It's an enabler of some use case, which can be, you know, making secure login to your bank or anything like that, or sending messages, you know, controlling a wind power mill or something like that to have good output. So what are those end use cases that we want to make sure that they work end to end, where PKI or what we do is just a small part? So we started this interoperability project to investigate these end-to-end use cases a bit more. Of course, based on TLS, typically message signing and validation using CMS or cryptographic message syntax, certificates, testing storage formats among different libraries, and of course, hybrid composite certificates and a lot of different things. So a different way to look at this is when I started kind of imagining what are the end-to-end use cases I want to try to see if you can get it to work. You know, the slides started filling up faster and faster, starting with things like firmware verification, ending, of course, with secure communication with TLS and everything in the middle. You want machines to have, or IoT devices to have secure boot. You need document signatures. We're EU, so things like signed documents is a big thing here. So, and actually, you know, it's only taking each of these pieces in isolation, you can get it to work, you know, especially now. So say a year ago, it was a little bit more fiddling, a bit more work to get each individual piece to actually work. But now we have reached a stage where things are nearing maturity. So we want to see what can we do out of the box. Since I'm not so interested anymore in compiling OpenSSL myself to get things working, I want to, you know, how can I use this out of the box in kind of production use cases? And starting with PKI, of course, which is my home turf. So then you need, of course, you need a certificate authority, you need a hardware security module, you need also validation to be able to create things like OSSP responses, but also they have to be validated. So implementing this in a kind of larger scale, specifically around the hardware security modules, also kind of shows you that standardization is almost there. There is something called PKCS11, which many of you are familiar with, that has a new version 3.2, which is also still only in draft. But a few hardware security modules have implemented that, so you can actually code against the draft standard and it will work with a few HSMs. Then there is a couple of other HSMs that use what's called vendor-defined mechanisms. They don't implement the draft standard, so you have to code specifically for them with some if statements. And then there are yet other HSMs which use arguably a more modern REST API-based approach. So when you implement kind of wider support for all new algorithms, you end up with a kind of fairly complex implementation stack, which has both some ins and outs and ifs and buts, etc. So, but one of the most common questions that we get, or that I get, has been how slow will these new algorithms be? So just a quick answer on that. I've been working kind of testing different HSMs for the past years as they have come up. So 1 year ago, you could kind of start testing with one hardware security module, but now actually all vendors of hardware security modules have implemented ML-DSA, which is kind of the most or first relevant use case for me that works with certificates and digital signatures. And there it's clear that actually ML-DSA is in many cases actually faster than RSA. So the answer when it comes to at least kind of a high-level use case like PKI and validation is that the new algorithms perform better than the old algorithms, or at least if you're using RSA. EC is still typically a little bit faster, but not too much. So that kind of fear is also past us by now, so you can start using it. Another thing which not everyone is aware of is that the new algorithms like ML-DSA, they don't work according to the hash first and then sign like SHA-256 with RSA or SHA-256 with ECDSA, but you have to send the whole data to be signed, which does put limitations. Not if you're having small amount of data like certificates actually or bank transactions or such, there's no problem of sending those to the HSM. But if you're generating very large CRLs, which we do have users who generate half a gigabyte CRLs with definitely more than 10 million entries on them, and then actually streaming that to a possibly cloud-based hardware security module is not feasible. And since IETF has banned the use of hash ML-DSA, there is this thing called external mu ML-DSA, which is the only way to save this. And I found that currently there is one HSM out there that implements external mu ML-DSA. So today, if you're using large CRLs, then you might end up in trouble. But still, it's, I would say, like 10 megabyte CRLs is still good enough for, say, probably 99% of use cases. But there are a couple of use cases out there where you have to pay attention to what you're doing. And the other kind of really big use case is TLS, of course. Everyone wants to do quantum safe TLS, which have two components, encryption or key exchange, which exchanges your asymmetric or symmetric encryption key, and of course authentication, which is digital signatures. So, and we have been able to do this for a long time, but not really out of the box until, so Bouncy Castle, for example, have been playing around or implementing post-quantum cryptography since 2012, while OpenSSL came out this spring with support for ML-KEM and ML-DSA. So that's when things really started to kick off what you can do in, out of the box, which is has been my focus for the fall. So trying this out with what you can do with off-the-shelf stuff, not compiling, building OpenSSL 3.5 myself, but installing something out of the box and just getting it running. And today you can do that. Things like, well, very soon. What I've been doing, I've been testing with Ubuntu 25.10, for example, which is beta today, but will be out in final release by the end of this conference, which is nice. And of course, other operating system and distributions are doing the same thing. And the key point here is that they bundle OpenSSL 3.5. And the impact of that cannot be underestimated, I would say. So, there we are. So what you can do today or by the end of this conference is install a plain vanilla Ubuntu 25.10, for example. Install an Apache web server with the single command as usual. If you're used to Apache, like apt install Apache 2, configure a virtual host, give it a classic certificate, RSA or EC, and you can pop up your web browser. In this screenshot, it's from a Firefox web browser. Type your Control-Shift-I, go to network security and see that it uses ML-KEM 768 x25519 hybrid ML-KEM key exchange. So yeah, your harvest now, decrypt later threat is mitigated without doing anything, basically, except updating your Linux distribution. If you want to try authentication, you give your server an ML-DSA server certificate. That works, but you cannot connect to it with your browser because the browsers don't support ML-DSA. So that kind of works halfway, but not 100%. But if you're using an API client instead, like OpenSSL, of course, then it does work. So if you have an API endpoint, there's nothing preventing you from out of the box without doing anything, getting both ML-DSA authentication, client and server if you're doing MTLS, and ML-KEM key exchange for the encryption. It just works. And you can even automate. Today, many people use things like certbot to automate the certificate lifecycle management of their web servers, and this almost works as well. Actually, you can use certbot and Acme to get your ML-DSA certificate for your server, but certbot doesn't have the kind of the front end fixed to handle ML-DSA, so you cannot it has key type. By the command line parameters, the only key types available are, say, an EJBCA. But if you generate your certificate sign-in request with OpenSSL, you can still pass it through certbot and get your automatic deployment of your certificate on your web server. So this is kind of, with a little bit scripting, this also works. But that's, I even checked certbot's Git repo on Monday on the way here, so it wasn't there yet then. So what more can you do? Things like curl, so I'm from Sweden, the inventor of curl is from Sweden, so all that was also very nice. You can just install it and it just works. And what's this? You can also do it in Java. If you configure your Java to use Bouncy Castle as TLS provider, or JSSC provider as it's called, and plug in your Bouncy Castle libraries, it also just works. You get start up your Wildfly or something like that server and it's done. So there's a lot more to it, or there's nothing more to it than that. You can do a lot of things that just works today. The second kind of important use case when it comes to post-quantum cryptography has been signing, or specifically things like firmware signing to distribute software to devices. And also here OpenSSL played a key part because we've been working with Bouncy Castle, so we have been able to sign things for a long time with ML-DSA and other algorithms, but things like firewalls use an embedded Linux and which ships with OpenSSL to verify it. And if you can't verify it, then, well, the whole idea kind of falls apart. So, but now, of course, with OpenSSL, it just works as well. So you can do that. You can do CMS signing or cryptographic message syntax, which is the most common way probably to sign code which is then verified before it's installed. And yeah, it just works. Everything with attached or detached signatures, signed or unsigned attributes, if you're familiar with the CMS standard, it works. There will be stumbling blocks, which is kind of the highlight of why it's important if you're for migration to post-quantum cryptography to start testing your use cases, because you will find some things that doesn't work well. In our case, we tried timestamping. So Bouncy Castle can create timestamps, but OpenSSL currently can't verify it. And that's why I'm here, of course, to talk to the people, to Tim Hudson, and push them to, well, fix that in OpenSSL. So this is, I'll actually skip that part. And so I'm gonna skip hybrid certificates and talk about, you know, how we collaborate as well around fixing these stumbling blocks. So we're doing, you know, we have to reproduce an issue. So we've done that with comparing things like timestamps between Bouncy Castle and OpenSSL. And then you have to report it somehow. So I'm lucky I can go here and talk directly to Tim and talk about it. Otherwise, you work on GitHub, as we've seen this whole morning, right? And do it right. And then as a reporter, you need to respond nicely, and then you test things, fixes, close things, and actually partner with the project. So we all want to be a very collaborative community and partner to fix things. And so unfortunately, we see this as well in our open source projects. You know, you end up stopping there. You get some reports, but it's more or less dies, and you get an issue backlog, which is hard to work through because things, well, not everyone is patient to work through the whole cycle from beginning to end. So my time is soon up, so I will finish up with mentioning you will also take a look at what protocols you use, because some are quantum, you can leverage them for quantum safe today. Some really needs more work in standardization. In this case, you know, the old trusty SCEP standard isn't, well, at least if you read the standard, you would really want to do some updates to it, which is actually also work in progress. So to summarize, you know, is there time to procrastinate when it comes to post-quantum cryptography? I would say no. 2025 is the last time when you can kind of confidently say that, okay, we don't have to do anything, because now things are working out of the box, and next year, yeah, you can. It's time to start moving. Will you find issues along the way when you start testing things? Absolutely, yes. Is everything production ready? No, it's not, but some things are. Enough things are. Can you contribute to this? Definitely. Find the places where things doesn't work as you want, and report them and work together to fix it. Is it expensive, of course, to start testing? No, as you've seen, you can just pull down a lot of open source software now and more or less production ready. And hybrids and composites, which I didn't go much into, are kind of another story, which is not out of the box. Pure stuff out of the box, but not the hybrids and composites. Thank you.